Welcome to Cyclopod, showcasing work by early career geoscientists that is of interest to the cyclostratigraphic community. This podcast is made possible thanks to financial support of the International Subcommission on Timescale Calibration. Hi there, welcome to the 6th episode of Cyclopod. My name is David de Vleeschouwer and today our guest is Margriet Lantink. Margriet is working on her PhD at Utrecht University in the Netherlands. 2 years ago already, Margriet published a paper in Nature Geoscience that caused quite a stir, both in the cyclostratigraphic community and in popular media. A Dutch newspaper, for example, featured a summary of her work under the title "An Old Climate Secret in the Striped Mountain." Those stripes, they refer to the famous banded iron formations. And old, well, that is very old. The banded iron formation Margriet studied comes from South Africa, and they were formed in the earliest Proterozoic. For those of you who don't usually work that far back in time, that's almost 2.5 billion years ago. So Margriet, welcome to the show. You're laying the last hand to your PhD thesis now, so how is that going?
Yeah, well, hi, David. Thanks for inviting me. My PhD has been going great. Yeah, taking a bit longer than expected or hoped. So I keep telling myself I can finish it in 2 weeks. Yeah, I expect to finish before the Christmas holidays. So,
all right.
Yeah, looking forward to that.
Good luck with that. But at least the first chapter of your PhD is done, and it will be based on the 2019 Nature Geoscience paper in which you advocate a climate control for banded iron formations. Before we start, can you describe how the Earth looked like 2.5 billion years ago?
Yeah, I can. Yeah, so that's already a hard question, of course, because the farther we go back in time, the less of the geological record has been preserved. But so the idea is that this was an anoxic Earth. So about 2.2 billion years ago, we start to see evidence that oxygen appeared in the atmosphere for the first time, as well as in a shallow ocean, because of ultimately the evolution of cyanobacteria, so oxygenic photosynthesis. But then we are about 100 million years before that, where you see in the stratigraphic rock record from that period, which is preserved in places like South Africa and Western Australia. You see this massive deposits of banded iron formations, which extend laterally over hundreds of kilometers. And these have been interpreted as evidence for a largely anoxic deep ocean, which was rich in iron 2+ dissolved, because you need that to be able to transport iron over large distances. And so the idea is that these deposits, these banded iron formations, or in short BIFs, were deposited, in the first stable passive margin settings that started to develop around that time.
And so you already talked about the lithologies you encountered in South Africa, in the Paleoproterozoic rocks of South Africa. Can you say something about the rhythm that is preserved in those banded iron formations? At what depth scales do they occur?
So we went to South Africa, where you have Kuruman banded iron formation, which is a deposit of about 200 meters thick. So the first 2 days we went to the core library, because people mostly look at drill cores when they study banded iron formation, and there, because we had the question, is there any Milankovitch control on these deposits? And from cores it wasn't really clear, because you see a lot of variations. But when we went to the field, there you see in like the Kuruman hills very nice meter scale variations in weathering profile, we call that, so relief. So you see these exposed layers of reddish brown iron oxide rich BIF, and then alternating with intervals that are like more weathered away, so they're more vegetated. And this occurred on a scale of about 5 meters. And then we also saw this larger scale variation, which caused this hierarchical stacking pattern at a scale of about 15 to 20 meters.
And so you nicely described the lithology, but did you also use any proxies to mark or to identify that lithological rhythm you just described?
Yeah, so as I said, we saw these alternations in the weathering profile, So we made basically first a log of these alternations we saw in weather profile. So with the Jacob stuff, we measured, we have 1 meter of very poorly exposed lithology and then 50 centimeters of intermediately exposed BIF. So we did that at 5 sections, separated of 150 kilometers. And then, but in certain sections, we also described the lithology. We took samples, which we then took back to the Netherlands and analyzed with XRF. Based on this, we can say that these more indurated, well-exposed layers are basically more iron oxide, silica rich, and then the more weathered intervals are more like carbonaceous and shale-bearing intervals.
So that iron oxide versus carbonate-rich lithological rhythm, you link that to astronomical forcing, so insolation forcing. Can you explain why that climate control, that insolation control for banded iron formations is controversial and still is controversial?
Yeah, well, so it's funny actually, because when you look at the very old studies from the 1960s, 70s, you have this scientist, one called Alec Crandall from Australia, who described these rocks and marked the clear regularity you see in these layers. And he actually wrote this 1973 paper where he was proposing that this could be controlled by astronomical forcing. But somehow, this got forgotten in the common scientific community. I don't know why, perhaps because of the discovery of hydrothermal vents. So people started to see these deposits as chemical precipitates. Then they started to develop this model that the most of the iron came from like submarine vent systems. People are arguing for a hydrothermal plume or volcanic origin for the rhythmic banding. Also, because they can tell us about the evolution of oxygen and redox evolution of the ocean, people have really tried to look at the mineralogy and the isotope chemistry to say something about this redox evolution of the Earth. And for this purpose, people really wanted to look at pristine drill cores, because you don't want to have the weathered rocks, you want to have the pristine geochemical signal. And I guess also that's why people forget to look at the rhythmic layering that you really see actually in the field. So I wouldn't say whether it's controversial that there's just astronomical control, or whether it has just been sort of forgotten.
Yeah, good that you picked it up then. So I like to zoom in a little bit into the cyclostratigraphic results you obtained. You are talking about bundles that are about 20 meters thick, and then you identified ridges that have a thickness of about 5 meters. And you already mentioned the stacking pattern between those with a cycle ratio of 1:3 or 1:4. And then you use uranium lead ages to claim that these 5-meter cycles are related to the 405,000 year long eccentricity cycle. And then the 20-meter thick bundles, they would be related to a 1.6 million year very long eccentricity cycle. So how crucial was it to use uranium lead to redate some zircons from the Kuruman BIF to come to this interpretation?
Yeah, it was essential. The uranium lead. When we did the field work in South Africa, and we saw the rhythmic alternations. So we logged them and analyzed them with the time series analysis back home, and we wrote a paper. All the time we didn't have any idea about the sedimentation rate, or at least very little, because of available shrimp, multigrain zircon ages. Their precision and accuracy was not good enough. So the position rate estimates for these rocks were between 3 and 300 meters per million years. So it's funny, because the sedimentation rate was so uncertain, we formulated 2 or more hypotheses based on like the ratio of the 2 cycles, dominant cycles we saw. So basically wrote the entire manuscript already, and then the uranium lead ages came. And then it turned out that our second hypothesis, which was not necessarily the most preferred one, because the alternative we had was, of course, the 100 and the 400,000 year electricity cycle. So, but the uranium lead, they said, okay, yeah, this is really consistent with our second hypothesis.
That's a cool story on how such a paper comes into existence.
Yeah.
But besides those first-order sedimentation rate estimates from radiometric ages, you also have a handful of additional arguments to back up your astronomical interpretation. You write about the lateral continuity of the cycles, their stacking pattern, of course, but also the systematic shift in both lithological rhythms up section due to a change in sedimentation rate, and about their amplitude modulations. In your opinion, is there one of all those arguments that sticks out?
Yeah, so then I would just say the combination again of the uranium-lead constrained deposition rate that was really consistent with these 5-meter cycles converting to approximately 400,000 years. Because we know that cycle, well, via precession has a really strong influence on insolation, and that is the cycle that we know of, which is related to the orbits of Jupiter and Venus, which the period is very stable. So yeah, that is for me really the strongest argument, I would say. And then also when we know that we zoom in at the centimeter to decimeter scale, like Tremble, I mentioned previously, already described the sort of Calamina cyclothem, and this is then the scale of this is sort of consistent with climatic precession.
So if I understand you correctly, then you're ascribing the centimeter scale rhythms to precession.
Yeah, so I mean the classical mesobanding that banded formations are known for regular repetition of certain mesobands of a thickness of about 15 or 10 centimeters seems to be consistent with a climatic precession origin. But then in certain intervals of these Kuhlmann, BIF, and also in Australia, you have a clear precession scale imprint, but in other intervals it's not very well visible. So that is something we don't understand.
Yeah, something enigmatic. Now we come to the section of the podcast where we take a step back and where we pick out a special number and look at our science from a bit of a distance. This month's number is 1788. That's the year in which James Newton found the Siccar Point unconformity in Scotland. And one of his friends with whom he visited the outcrop would have said, "The mind seemed to grow giddy by looking so far in the abyss of time." It's quite a heavy quote, but Margriet, you are really doing cyclostratigraphy in the abyss of time, right? Looking at rocks that are about 2.5 billion years old. Do you sometimes become philosophical when you think about how our planet could have looked like back then?
Yeah, well, philosophical, I don't know. It's really nice to work on such old rocks and to use your knowledge from the present day and the more recent geological past with your imagination. That's really the nice thing about our work. Also, when you look at these rocks, it's somehow they look really familiar, like present day, or like very recent rocks, but they also very odd. So that is really I like that. And so I would say definitely more a supporter of uniformitarianism, but actually more of Milankovitch theory, right? So the Earth is a dynamic system. So, and this is something we have to keep in mind, I would think, when we work on the early Earth.
Thanks, Margriet, for this little in-between science philosophy section. Let's go back to the science now. So if you look at the paleogeography of the Paleoproterozoic, you have Australia and South Africa close together. And in your paper, you hint towards the possibility of making cyclostratigraphic correlations not between sections 250 kilometers away, but also between Australia and South Africa, so multiple thousands of kilometers away. What do you infer from that in terms of paleoclimate?
Yeah, so first of all, the question is how far were they apart when the banded formations were deposited? Like stratigraphic studies and also paleomagnetic reconstructions have been trying to argue that there are maybe these banded formations were simultaneously deposited in this Transvaal Basin in South Africa and in the Hammersley Basin in Western Australia in either partly enclosed basin or at least along the same passive margin of a larger supercraton. 2.4 billion years ago, you had the first supercontinent, Superia, forming also combined with other cratons located from, for example, Canada. And this combined with the strong eccentricity, thus precession control, we see in these deposits located at around the equator or at least low latitude. Yeah, the first thing you start to think about is, of course, a monsoonal control, because we know also that at mid to low latitudes, that's really a system that is strongly responding to astronomical forcing.
So if you are saying monsoons, I start thinking about nutrient fluxes from the continent to the ocean. Could that have played a role in explaining the alternation between iron-rich and iron-poor layers?
Yeah, perhaps, yeah. So at the long period eccentricity scale, we see these alternations not only between iron oxide rich and iron oxide poor intervals, but the iron oxide poor intervals are also more shady. That could indicate that you had these alternations of continental influx, which triggered periodically productivity. But then the question becomes, does that result in more deposition of iron oxides? Because it could, on one hand, trigger the anoxygenic photoferrotroph bacteria that were living there in the case of an iron-rich water column, which then oxidize the iron and this precipitates down. On the other hand, you could argue that increased productivity would induce more organic matter deposition at the seafloor, which is then converted to carbonates because of dissimilatory iron reduction, we call that. So this is a diagenetic process where you reduce the iron oxides together with organic matter, you form iron carbonates. So this is these mechanisms, you have to really, to solve this, you really need to look at the precession scale, because this is the direct climate influence. And we also do not know anything yet about the phase relations between the astronomical forcing, the monsoonal influence, and the lithological changes.
What would be a possible strategy to resolve those phase relationships? Imagine that you have unlimited funding. What would you do to unravel this chain of phase relationships?
Yeah, so first of all, just investigate more rocks and specifically look for intervals where this precession signal is particularly clear from different intervals. For example, iron oxide rich intervals at the eccentricity scale. And then, on the other hand, I would collaborate with modelers, both biogeochemical modelers. Maybe you can look at how the biogeochemistry response would respond to increased nutrient influx, diagenetic processes, and also perhaps climate modelers. I don't know whether this is realistic for such a long time ago where we have very little constraints about the paleogeography, but to do some sensitivity testing of what a monsoonal response would be given a certain land-sea ratio.
Thank you, Margriet. Well, realistic or not, it's a very cool dream or a very cool vision to end this podcast on. At this point, I would also like to thank our audience for listening to the 6th episode of Cyclopod. I really enjoyed talking to Margriet about her Nature Geoscience paper and about the oldest cyclostratigraphy that has been covered by Cyclopod until now. And honestly, I think the record that Margriet just set will stand for quite a while. What I really liked about Margriet's cyclostratigraphic work is that she made a very good case for a climate control on banded iron formations, just with a handful of basic observations, good uranium lead ages, and detailed logging. So Margriet's paper might be quite provocative or controversial, and I'm pretty sure that not everyone who has read the paper will like Margriet's conclusions, but at least the paper adheres to the entire set of guidelines for a good cyclostratigraphic study, as we described them in the framework of the Cyclostratigraphy Intercomparison Project. Thank you for listening, and see you next time.